Hello friends, I welcome you in lecture number 16 on relations. In this lecture, we are going to discuss this question on operations on relations. This question was asked in GTU Winter 2021 exam. As discussed in lecture number 15, that relations are nothing but sets, and therefore we can talk about different operations of set theory on relations also. In the last lecture we have discussed about two operations on relations. One is union and another is intersection operation. So here also we are going to discuss this question, which is mainly focused on the intersection operation on relations. Let capital L denote the relation less than or equal to, and capital D denote the relation divides, where x dy means x divides y, that is x and y are related with respect to relation D, which is divides relation, and capital L denotes the less than or equal to relation, that is x ly means x is less than or equal to y. Both the relations denoted by capital L and D are defined on this set having these four elements 1, 2, 3 and 6. We are asked to write L and D as sets and then find their intersection. So this is very easy question. First we denote given set by say capital X or say capital A. A denote this set 1, 2, 3 and 6, and first we write down the relation L, which is less than or equal to. So what is meaning of this less than or equal to relation? This means we have to collect all those ordered pairs x, y such that x, y are elements of set A and x is less than or equal to y. L is a relation on set A, that means L is a subset of A cross A. A cross A means Cartesian product of this set 1, 2, 3, 6 with itself 1, 2, 3, 6. The Cartesian product of this set A with itself will have 16 ordered pairs. Out of those 16 ordered pairs, we have to write down those ordered pairs x, y for which x is less than or equal to y. So first we write down all those ordered pairs x, y for which this condition x less than or equal to y is satisfied. So for that we start by fixing this 1. We fix first component 1 and we vary all these as second components 1, 2, 3 and 6. So first order pair is 1, 1 and we know that 1 is equal to 1. So this condition is satisfied for this order pair 1, 1. So we will write 1, 1, then 1, 2. So because 1 is less than 2, order pair 1, 2 also belongs to relation L. Similarly, order pair 1, 3 is also a member of L, and order pair 1, 6 is also a member of L. All these ordered pairs satisfy this condition. X is less than or equal to y. Here x and y are equal, and in all these ordered pairs x is strictly less than y. Now we start with 2 as first component. So first order pair is 2, 1, but 2 is not less than or equal to 1. So we will not write that order pair. Then 2, 2, because x is equal to y, x equal to 2 and y equal to 2. 2, 2 is also a member of L. Then 2, 3 is also a member of L because 2 is less than 3, and 2, 6 is also a member of L because 2 is less than 6. Then we consider 3 as first component. So 3, 1 is not member of L because 3 is not less than or equal to 1. Similarly 3, 2 is also not member of L, and 3, 3 is member of L. Both the components are equal, and 3, 6 is also a member of L because 3 is less than 6. Then 6 as first component, so 6 is greater than 1, 2 and 3, so 6, 1, 6, 2, 6, 3 are not members of L, and 6, 6 is a member of L because x is equal to y for this order pair 6, 6. So this is the relation L which we have written as sets using this condition. Similarly, we are asked to write down the relation D. To write in terms of set, relation D is the divides relation on the given set A. So first we write down order pair xy such that x and y are elements of A and x divides y. X divides y. So here also we have to check for each and every order pair. We will write down order pair xy as a member of D if x divides y. So again we start with first component as 1. So first order pair is 1, 1 and we know that 1 divides 1. So we write down 1, 1. Second order pair is 1, 2. So 1 divides 2, therefore we write down 1, 2. Then 1, 3. 1 also divides 3, 1, 6, so 1 also divides 6. So with 1 we have 1, 1, 1, 2, 1, 3 and 1, 6 because 1 divides every positive integer. Now we fix 2 as first component and first order pair is 2, 1, but 2 cannot divide 1, so 2, 1 is not member of D. Then 2, 2 is member of D, so let me write 2, 2. Then 2, 3, order pair 2, 3, but 2 cannot divide 3, so 2, 3 is not member of D. And 2, 6, 2 divides 6, so we write down 2, 6. Then we fix 3 as first component. 3, 1 is not member of D, 3 cannot divide 1, similarly 3, 2 is also not member of D. 3 divides 3, so 3, 3 is member of relation D and 3 divides 6 also. So 3, 3 and 3, 6 are elements or members of divides relation 3, 3 and 3, 6. Then last possibility is 6 as a first component and we know that 6 cannot divide 1, 2 as well as 3. So the only possible pair is 6, 6. So now we have written L as well as D as a set. They are the sets of ordered pairs and all those ordered pairs are from this A cross A. We are writing those ordered pairs for capital L for which x is less than or equal to y, and for D we are writing those ordered pairs xy for which x divides y. So this is the first part which we have to write L and D as sets, and then we are asked to find out intersection of these two relations. So we will search for those elements which are present in both the sets. So we can see 1, 1 is present here, 1, 2 is also present in both the sets, then 1, 3 is present, 1, 6 is also common, then 2, 2 is also there, and 2, 6 is here. 2, 3 is not common, 2, 3 is in L but it is not in D. 3, 3 is common, 3, 6 is also common, and 6, 6 is also common. So we can see all the elements of D are in L, or the members which are common to both the relations L and D are nothing but elements of D, or we can say that D is a subset of L. Therefore L intersection D is equal to relation D. Intersection of both the relations is relation D. And this is obvious also that whenever some element divides another element, suppose A divides B, then A is less than or equal to B. So therefore you can see all the elements of relation D are satisfying this condition, A less than or equal to B. Therefore intersection of these two relations is capital D. But here we are asked to write down L and D as sets first. Therefore we have written L and D as sets. Otherwise we can directly write down that L intersection D is D, because whenever an element xy is present in relation D, that means x divides y, and if x divides y, then x is less than or equal to y, and therefore this is present in relation L also. So every member of relation D is also a member of relation L, and therefore D is a subset of L, and therefore D intersection L is equal to D. But here in this question they have asked to write down capital L and D as sets. Therefore we have written this L and D as a set, and then we have written their intersection. So they ask this type of questions on operations or relations in GTU exams. So this is all about this session, and we will continue this series on relations in upcoming lectures. Thanks for watching.